So welcome back, everybody. And this is our last session this semester. Sadly, it's come to an end. I always find it very, a little bit, how to say, strange or sad. I don't know which kind of word to use when the semester is over, because we get to know each other. And being at the lab is always very fun. However, what we plan to do, even if this is the last lecture, we plan to have lab sessions next week. And if somebody wants to have, let's say, 1 or 2 sessions the week thereafter, although the different TAs may be busy with exams themselves. So, but next week we plan to have lab sessions from 10 to 4, if people wish to swing by. And so that will be Wednesday and Tuesday as our regular times. So feel free to swing by if you want, but we will not start at 8 o'clock. Because we've seen that many of you, when it gets getting close to the end of the semester, people are busy with exams, etc., etc. So just feel free to swing by or just send us an email in case there are things you're wondering about. Now, I just wanted to say one other thing about the project, the final one. You've probably seen that we have this numerical solution of differential equation. That's one specific path. And for those of you, this is a project which has been tailored more for people who have studied differential equations. And some of you may have taken a course like Computational Physics 1, where you discuss finite difference schemes. And you can then just reuse what you've seen in that course. Or if you're taking a course which is called Numerical Partial Differential Equations at the Department of Mathematics, which actually runs simultaneously with this one, you can actually combine what you've done in that course with this one. For that specific part, you can actually reuse your code from project number 2. Now, when it comes to the other possibility, which is very much like you doing research on specific data, then as we discussed during the lab sessions, this is a place where you can explore new methods using libraries like Keras with TensorFlow or PyTorch, or codes you've written before, or scikit-learn. So a typical setting could be a classification problem where you use random forests, you use boosting methods, neural networks, convolutional neural networks, or whatever, and just test the different methods and see which one gives the best result. So some people have only studied decision trees, random forests, etc., and studied how these different methods actually describe the data. That's another possibility. So, but discuss with us what kind of options you want to study in the final project. I think that's always useful. And also what kind of data sets you want to study. And we mentioned during the lab session that this data set, which is called Kaggle.com, is a very useful one because it contains many cases where the data sets are already made or ready for usage in, let's say, scikit-learn or TensorFlow or PyTorch, etc. So one thing you should try to avoid is actually to have a data set where you need to do a lot of manipulations to get the data set ready for usage with a machine learning algorithm, because that can often take a lot of time. So if you look back at project number 2 with the neural network and the Wisconsin data, in that specific case, this is data which is already ready for you in terms of a design matrix and in terms of the output or target values. And you didn't need to actually set up the design matrix yourself or the data set. So just think of that in case you wish to study some data sets which are relevant for your thesis or some data sets which you're interested in. If you're going to need a lot of time to prepare the data or massage the data, as we often say, so that it's ready for a given algorithm, then you should be a little bit careful with your time. Okay, any questions about the last project? So we want you to be able to research and explore things with the methods we have discussed. And if you are a little bit in doubt, don't hesitate to send us an email or just meet up at the lab sessions and discuss the project. So the last topic this semester is actually the topic about bagging methods or these ensemble methods, random forests, and boosting. So we will spend some time on boosting today. The basic philosophy is actually very simple. But before we do that, let's quickly say something about the things which we went through last week. So last week, we actually discussed decision trees, and decision trees are often used as a weak learner in many of these ensemble methods. And you saw last week we introduced this bagging, which is bootstrap by aggregation. So we are just simply bootstrapping our data set. So every time we make a new bootstrap data set, we train a tree. And then we do the bootstrap, let's say 100 times. So that means that we have a forest of 100 trees. We can really claim this is our own forest. It's the first time in our life where we probably can make our own forests easily. The problem with the bootstrapping and aggregation is that if you think back to what we discussed last week with decision trees, is that if you have a dominant feature, that feature will define the root node of the tree. That means that the trees are going to be lookalikes. It works pretty well, but it can easily lead to overfitting sometimes. And a method which avoids this is actually what's called random forests. And the philosophy behind random forests is, again, extremely simple. But let's just remind ourselves about this bagging or bootstrap by aggregation. And the best way to look at that one is to write your own code with Bootstrap, as we did back in project number 1. So the code which we looked at last time, if we now peel away that one, so we had a data set with 100 points, and this is a case of a regression case where we want to fit a function which you probably never seen before, or you've seen it so many times that you are just fed up with it. This is a function which we used, which we saw when we discussed the bootstrap method. And in this specific case, now what I'm setting up is this exponential, and then I have a x which goes from -3 to +3. I do 100 bootstraps, and what I also do is that I make the tree deeper and deeper. That means it has more and more nodes, and the more nodes you have in the tree, the better you can reproduce the data. So a tree which fits precisely the data leads normally to overfitting. Now, in general, a decision tree is not made very tall or deep. So you start with a root node on the top, and then you go down till you have a Gini factor, as we discussed last week, or an entropy, which is 0 for each branch. And then you would stop the training, but you can make the tree shallow or not very tall. And that means it's going to be, sometimes it's going to be only a little bit better than just tossing the coin if you have a binary case. So a tree can be used as what we normally call a weak learner. And that's the basic philosophy behind boosting methods, which we will come to pretty soon now. So this specific case, we run through trees with different depths. And in our case, we make the maximum depth of the tree 8. So we are having actually 8 main nodes. And then we transform the data, we scale them, and then we set up a simple tree, which has a max depth of 3. And then we do the bootstrapping. So for every bootstrap, we actually produce a new sample, and then we fit a tree to that sample. And that gives us a prediction. And then we calculate the bias and the variance and the total mean squared error for that specific case. And what we saw last time, in particular also the simple tree with depth 3 has a mean squared error 0.56, which is perhaps not very impressive. And you see in this case, you get a variance which is now small, but there seems to be a slight increase here. So when I reach a depth of roughly 5.6, this variance and the mean squared error seem to stabilize, but there is a clear tendency that it's growing up. This is becoming larger. So this is a typical example of how you would build a forest. However, the problem here is that since you may have a dominant feature in the data set, that means that the root node and most likely all the other nodes will be pretty similar. So the trees will all be lookalikes. So this could be a birch tree forest, or it could be a fir tree forest, or whatever. Now, the way to make different trees is called random forests. And the algorithm is very simple. So at the heart, you have your decision tree algorithm, which we discussed last week. That's always there. But then the random forest way to avoid this kind of recipe where you grow equal trees is actually to build a set of decision trees on bootstrap training samples. But when you build these decision trees, each time you make a split in a tree, then you make a sample, a random sample of M features. So if you think back to the cancer data you had in project 2, you had 30 features, right? So M would be the number of features you have. So instead of you building a tree with all the features, and then clearly if you use all the features, the dominant feature will be the one which defines the root node, as we discussed last week. But then what you could do now is you could pick randomly just the square root of the number of features. So if you take 30, you take the square root of 30, which is a number closer to 5.5 something. And then you would just take these features as a way to grow the tree. So instead of taking all the 30 ones, you take the square root of 30, and then you pick them randomly, and then you build a tree. So that means that there may be a dominant feature there among these 5, or the square root of 30, which you then would use to grow that specific tree. The trees will not be that tall. They will actually be simpler in general. But then you can grow a forest which has different trees. So you see the recipe is extremely simple here. So every branching, you just keep randomly. You select randomly the types of features which you want to keep. So the reason, as you can see here, is that suppose that there is one very strong predictor of feature in the data, along with a number of other moderately strong predictors, then in collection of bagged variables, the importance random forest trees, most or all of the trees will use the strong predictor in the top split. So that means that all the so-called bagged trees will look quite similar to each other, and we want to avoid that one. And the algorithm here is pretty simple. So you set up a forest of B trees, like we did previously. We had 100 bootstraps. And then you draw a bootstrap sample from the training data, like we did in the case of bagging, exactly the same. But then you grow a random tree based on the bootstrap data by repeating the steps outlined. So we would first select m less than p variables. It's often done by taking the square root of it. And then you pick the best split among these m features. And then you would typically use the cart algorithm we discussed last week. And then you create a new node. And then you split this node into daughter nodes. And then you output then the ensemble of trees, and you make predictions for either regression type of problem or classification type of problem. Exactly in the same way as we did before for bagging. So the only difference between a random forest and bagging is that you have less features every time you grow the tree, and you pick these features randomly among a smaller selection. And that's it. So you could actually write this code very easily if you have your code for a decision tree, which we discussed in detail last week. And then you could simply just perform the training by selecting less features. Does that sound okay? It's not actually that difficult. You see, these trees, they don't have very much involved mathematics. So random forests also do a pretty good job, and tend often to avoid overfitting. So let's take a look at this when we use the cancer data, which we had in project number 2. So in this case, I'm comparing this with the logistic regression. And there is a topic which we haven't covered this year, which are called support vector machines. And in this specific case, I'm using the support vector machines for classification. Then I have the decision tree, and then I have my at the end here, I have my deep tree with random forests, which I'm actually setting in here. So this is a random forest model. And then I will simply use the random forest classifier, which I have from scikit-learn. So if you wish to use, this is a very popular method actually. And it belongs to the pre-deep learning methods and does normally pretty well on many, many classification problems. On regression problems, my experience is often that decision trees and variants of decision trees don't do that a good job. But let's look at a classification problem which we have encountered many times. And just let's run this code here. And you will see now that my decision tree, this is a shallow tree, is actually not very good, it's 0.88. This is my logistic regression, 0.96, support vector machines gives 0.96. But then you see this random forest actually does pretty well. And again, the algorithm is extremely simple. So in my case, in this case, actually, I grew 500 trees. So this is a variable which you can set up. And you can also decide how shallow or how deep the trees should go. So you can define the max number of nodes or the max number of leaves you want to have. So these are parameters which you can set in the input to scikit-learn here. And as I said, to write your own code is actually not that difficult. This is something which people have done as a variant of Project 3. They asked whether it was okay if they wrote their own decision tree code and wrote their own random forest code. So we want to give you as much flexibility as possible when you're dealing with the different projects or the different variants. So if this is something which you find interesting, feel free to follow that path. Or alternatively, use different methods, and this will be one of the different methods for classification problem, where they actually work pretty well. When we come to boosting methods, we're actually going to get an accuracy for true false and true positive and true negative, which is equal to 1, so which is quite impressive. So these boosting methods, as I mentioned last week, they tend to win many of these classification competitions. So you will see on this website, kaggle.com, that even companies, if they want people to analyze their data, they would put the data online and then have a competition and see who can classify their data the best way. But you see the results here, actually, this is a pretty decent one on the cancer data. So let me ask you about project number 2, by the way. Did any one of you get something like this with your neural network code? 98% on the Wisconsin data? Anyone who did that, roughly? Yeah. So I think most of you were in the ballpark of these numbers. But you see, this method is just so simple. It's just a decision tree, which you grow many, many times. And it gives normally a pretty good result on classification problems. We can continue like this. So you see the ROC curve is also pretty good. You're rather close to 1. So this is the true positive rate, which we discussed earlier during one of the lab sessions, and plotted against the false positive rate for class 0 and class 1. And you see that the curve is actually giving you a pretty good result already here. And the same with the cumulative gain curve. So you can compare this with bagging. So scikit-learn, instead of you writing your own code, which I showed you earlier, you can have a bagging code, which is a bootstrap with aggregation for classification and for regression. And scikit-learn has a variant, which is now called the bagging classifier. And then you decide how you split the tree, the max leaf nodes, and then you start randomly. You're setting up 500 trees, and you're having a bootstrap. And the classifier is also doing a pretty good job. And if we run this code here and compare that to what we had earlier, we're getting something like 97%, which is not so, or 98%, which is not so bad. So when it comes to random forests and decision trees, you see the mathematics is not very, very difficult. Now, what I wanted to move into now is a quick introduction to these boosting methods. So boosting methods are methods which have a little bit more mathematics. And what they do is that they take often a decision tree as what we call a weak learner. So you could think a parallel to this one could be you improving your linear regression case, starting with a first order polynomial. And then you improve upon that iteration by iteration. So you would start with something which is simple, and then you build upon that. And one of the reasons why people often use decision trees is that they require few floating point operations. You don't make a very tall tree or deep tree, if you think of the root node as a top node, which means that it's easy to do the first training, and then you can improve upon that. So let me try to give you a feeling of how this iteration is done. So this approach which you see here is something which is used widely when you try to improve upon a first guess. So let's look at the basics of the boosting methods. So boosting in this case means that you take a crappy method and then you boost it up. You make it better iteration by iteration. So this is where the meaning of boosting comes in. So you're just using a very simple method and then you just boost it up gradually. So let's take a look at the mathematics of boosting. And let's look at a simple thing here. So I'm going to switch. You will find some of it in the slides as well. But let me now just bring it up here. So if we look at this boosting methods, so the whole idea is as follows. And let's take the mean squared error as an example, because that's pretty intuitive to build up our feeling of what a boosting method does. So basics of boosting. And let's take the mean squared error as an example here. So we take the mean squared error. And if you look at the mean squared error, the way we have defined it is either with a factor 1/n, or we can take it away, which is what we did typically in neural networks. So we have the target value y of I, and then we have our approximation fx of I squared, right? So this is what we met in the very beginning of the semester. Now, what we can do now, so the approach here, or the basic philosophy, that is to improve that is improve this f of x of I iteratively. Starting with a very simple approach or simple method. Starting with a simple method. And what you will see when you do the regression case, and if you start with a first order polynomial, is that gradually as you move on, you will build up higher and higher order polynomial degrees of freedom. So this is just a way to build up a more complicated polynomial starting with a first order polynomial. But let's just look at the basics. So what we're going to do now is simply to say that this one is equal to some function m of x of I. And this is now given by a sum from I equal 1 up to some m. And where we then have a parameter of beta of, or let's put a little m here, of beta of m. And then I have my function b. This is a function of x of I. And it depends on some parameter gamma of m. So what we are going to do now is to define the optimal beta and the optimal gamma, we have these hats on it, by minimizing our cost function, which now could be the mean squared error. So we have a cost function which depends on these beta and gamma parameters, where these beta and gamma are now parameters which define this function f of m. So this would be what we could do now is to start with a function at m equal to 1. So if we start with the little m equal to 1, then we would have an f of 1 of x. So I'm not putting an x of I, I'm just looking at a value x now. And that could be some f0 of x plus some parameter beta 1. And then this function b, which is our model of x and a gamma of 1. So we could now assume that this f0 of x, we could just start with 0. So if we just start with 0, then what we would do then is perhaps to make an example here. Example for b, which is simply given by 1 plus a parameter gamma times x. Just a first order polynomial. Okay? So what happens then is that what we would have then would be that when we're setting up the cost function, we would now have for every iteration, so for every iteration m, what we do then is that we define the optimal beta m and the optimal gamma m. And that's given by the optimization. So we would do this optimization at every iteration. And this is given by beta and gamma. And if we now look at the mean squared error, which we had, so this just continues on the next line. So we would have 1 over n, and then we have a sum over I, and we have y of I minus, and then I have my f of m minus 1. So if we start with m equal to 1, this would be f of 0, which we put to 0. So this would contain the value x of I minus, and then I have a parameter beta, and then this function b, and then I have my x of I, and then I have this parameter gamma, and this is squared. So if we now plug in this simple approach, in this example, we have a very simple function. So what we would have then would be 1 over n, and then I have the sum over I, and I have y of I minus, and then I have my f of m of x of I, and this is minus, and then I have a beta, and then I have 1 plus gamma times x of I, and this is squared. So the optimization here is something you can set up with analytical gradients if you want to, because if you take now the derivative, so every time you perform an iteration m, you optimize and find the best parameters. And then you use these parameters to define the next function. So if you look back at what we had, when you have done one iteration, then you have found a specific function here, beta of m, and then you would simply sum up all these functions up to a given value of m. And the final m is what defines your best approximation to this specific value or to this specific function. You see the basic philosophy here? So every little m, you perform a optimization, which means that you calculate the gradients and find the optimal parameters beta and the optimal parameter gamma. And then you build the new function, f of m, given by the old one, plus the new parameters. And then you keep going till you stop at iteration upper with the uppercase m value. So if you look at this specific case, if you take the derivatives, So for this specific case, for every iteration now, for every small m, what you would calculate then would be the cost function and the derivative of the cost function with respect to the parameter beta. So this will be simply given by -2 divided by n, and then you have a sum over I, and then you have 1 plus gamma times x of I. This is just a derivative. And then you have a y of I minus, and then I have my f of m minus 1, the previous value, minus beta of 1 plus gamma times x of I. And you want this one to be 0. And then you also have a derivative here of with respect to gamma, which is also given by -2 of n, a sum over I. And then this expression is a little bit simpler because I have a beta x of I, and then I have y of I minus beta of 1 plus gamma of x of I. And this is also equal to 0. Now, you don't have, for this case, I don't think you have an analytical solution here. So what you would typically do then is to use automatic differentiation. You would set up the gradients in every step. You would find the roots of the gradients, and then you have the optimal parameters. And when you have the optimal parameters, so with the optimal ones, so with, at that specific iteration, with beta m optimal and gamma m optimal, what you do now is that you define this fm of x, which is equal to the previous value, -1 of x. So you have determined that one. And you would typically start, you can start with 0 here if you want to, plus this beta m hat multiplied with this function b, which now contains x, and is a function of this gamma of m, the optimal value. So that's the next one. And then you would then perform a new iteration, and then instead of m, you have m plus 1. You calculate the gradients again. You find the optimal values, which optimize these cost functions, and then you keep going till you have reached the final value. So that means that at the end, so you keep going, and then you loop from m equal 1 to m equal little m. And you would typically set the stop for that specific case there. So that's the basic algorithm here. So you would then, if you want to set up the algorithm, this is pretty simple. And you see now that instead of having a polynomial, you could take a decision tree. And you could take a shallow decision tree, which is, so this function b is a function you want to be easy to calculate. So it shouldn't require so many floating point operations. So if you think of a first order polynomial, you could use that. Or you could take a shallow decision tree with 2 to 3 nodes at most. And that's easy to train. And then you will just keep building upon this model. So the basics of boosting models is you just boost the crappy result you start with, which could be only slightly better than tossing a coin, right? And then you keep improving upon it. You see the philosophy? It's pretty simple, right? So this was for regression. And afterwards, I'm going to show you how you can do this for classification. The classification case is a little bit more interesting. And there are many, many ways you can do that. But the classification case, what you do then is a very simple recipe. You give more weight to the cases which are misclassified. And the cases you classify correctly, you just give a small weight. So that means in this training and boosting, you actually boost the errors. And then you train on those cases which you didn't do well with. So you put focus, you drive the good cases to 0, and then you just boost the bad cases. And then you keep training till all the bad cases are gone, and you do a perfect classification. So these algorithms are very intuitive, and when you see them here, you will see that it's very easy for you to write your own code. Like the method we are going to encounter now for classification is called ADA boosting, not ADA gradient, but adaptive boosting. And we will see how that goes through. But let's set up the algorithm for the regression case, or the general algorithm, because it's pretty straightforward. So the algorithm, which we would need to set up, runs as follows. So you would set up a initial value. So you would initialize, we always have to do that, initialize this f of x and or f0 or y. And this is often actually set to 0. And then you need to define the cost function, and m, the maximum number of iterations you want to make, and this function b, which now depends on x and gamma. So you need also to initialize these values, initialize gamma and beta. So you can need some initial value you start with. And then you have a loop here. So for I or m equal 1 to uppercase m, then you would have the first step, you optimize and compute this beta m, define the optimal parameters, the pairs here, and that is just the argmin of given values of beta and gamma. And then we have the cost function, which depends on beta and gamma. And here you can use automatic differentiation, you can use JAX, autodiff, whatever you want. Then the next step is step B. Then you would define or set the next one, fm of x, which is a function now of fm of x of gamma and beta. And that is simply given by fm minus 1 of x, and then we have gamma of m minus 1 and beta minus 1, m minus 1, and plus this new function which you have determined by beta of m, and then I have the function x and gamma of m. And then when you're done then is actually when you've gone through all the iterations, then the final function which you have when you're done with this, so you have an end for, and then the final thing is to return this fm of x. And that's the function which you will use to make predictions. So when you have this final f, that's when you can then start making predictions, okay? Then you have trained a model where you have used a very weak learner. It's normally called a weak learner because sometimes if you do, let's say, a binary classification problem, you could have a weak learner which is just barely better than just tossing the coin. And then you keep improving upon that. You can obviously make the weak learner a little bit stronger, and that's up to you. So you can play around with different possibilities here. Now, let's now look at the class. This was a regression case. Let's look at the classification because there are different ways by which we can do that. So let's see how we do the classification. And as I said, the classification, if we now take the binary case, which is normally the easiest one to view, if we take the binary case, what we are going to do now is to put an emphasis in the different iterations on the misclassified cases. Okay? So this is going to be the basic approach we take. So let's now take the classification problem. So boosting and classification, and we will stay with a binary case. And classification. And here as well, you will be surprised by the simplicity of the algorithms. So let's now suppose that we have a data set of D, which is now given by some x0, y0, x1, y1, etc., up to some final xn minus 1 and yn minus 1. This is our data set, and where each of these x's is associated with a class, with this y of I. So let's now make a simpler case now where y of I can be minus 1 and plus 1. So these are the outcomes. You can set it to 0 and 1. This is up to you. Okay? And you will see why I put it to minus 1 and 1, because that gives a very simple algorithm for the case which I want to do now. So what I want now is also to have a set of each of weak classifiers, set of weak classifiers. And I'm going to call this set for B1, B2, up to some B of M, or rather this uppercase letter M, where each one of these, a Bj of some x of I, gives now results which are either minus 1 or plus 1. So this is my weak classifier. So I could start with a classification tree, which has 2 or 3 nodes, and stop there. So my weak classifier. It normally doesn't do a very good job, but it does a rough estimate. And then I want to use the same philosophy now and build up a model which is based on that. So what I'm going to say now is that my model which I'm building up is going to give me a new function, and I'm going to call this function for C. So I previously had F, but now I'm going to have C for classifier. Okay, so F for a continuous function, and now I have a C for a classifier. And in my case now, I'm going to have a classifier x of I, which is given by my previous classifier, x minus 1. And then I'm going to have a parameter alpha of m, and that's the one I want to train now. And then there is a function, b of m, of x of I. So it looks very much like what I had before, but I don't have this parameter gamma. No, I only have a parameter alpha. And this is the kind of approach I want to do now, so that my final C of m of x is now going to be given by the sum over all these i's equal 1 up to m of C of m. No, sorry, C of I here, as a function of a given value of x. Now, how do we actually find these parameters? So how do we find? These alpha m's? So these are going to be the parameters now in my weak classifiers. So we are going to define an error. So we define an error, and we want to give an emphasis on the wrongly classified results. So define an error, and this is a quantity which we now are going to optimize. And I'm calling this an epsilon error, which is simply going to run over all my data up to n minus 1. So this is all my data, which I have. And this is given by e and minus y of I. So this is the target value. And then it's multiplied with c mxi. So if you look at the argument, I know that y of I takes the value minus 1 and plus 1. Then I also know that this Cm is going to produce either minus 1 or 1. So now comes a question to you guys before we take a small break. So correctly classified. Cm of x times y, what should I get if it's correctly classified? Any good answers to that? Which value, if I multiply my output, yeah, just +1, exactly, because if it's -1 and I classify it as -1, it's -1 times 1. So if it's correctly classified, I should get +1. And when it's wrongly classified, CMX of y is equal to, can you see that? Yeah, you can see that, yeah. What should I get if it is correctly classified? No, sorry, if it's wrongly classified. -1, yeah, exactly. So this is an extremely simple function. So keep in mind also that if you look at this, this is just one way to calculate the error. So what you see now, if it's -1, I have e to the power of minus. So that means that if I put e to the power of minus times minus, this is plus. So I have the exponential with a positive argument. So that becomes large. So if I classify wrongly, I give a lot of weight to the wrongly classified results. If on the other hand, I have minus, or no, so positive, correct classification, I get e to the minus something. And that means that I give less weight to the correctly classified ones. So what I want to do now is to drive this misclassification error to 0 as quickly as possible. And this is just one function. There are many different ways of giving a given weight to the misclassifications and the correctly classified ones. This is the simplest possible one. You see now that you have a positive argument if you misclassify. So that means you carry with you a stronger, in the next iteration, you carry with you a stronger weight on the bad guys. So after the break, I'm just going to show you how you can find, if you now look at the equations we have, after the break, by optimizing this function here, we will find an expression for these alphas. And that leads to a famous algorithm, which is called ADA boosting. And you will see that's very easy to implement. And it does extremely well on classification problems. Surprisingly well, given its simplicity. And sometimes you may ask, why should I do these complicated deep learning methods when I can have methods like these, which do so well? And you will later see with boosting methods, they're also doing pretty well. So boosting methods, gradient boosting, is actually a slight change of what you see here, but where you actually train a gradient. So this function B of m is now replaced in gradient boosting, is replaced by the gradient of the cost function, iteration by iteration. And you want to drive that to 0 gradually. So the philosophy of these methods are extremely simple and they're very easy to implement. Okay, I went a little bit over time. That was a little bit deliberate. There is coffee here, and we just take a small break, and I will use half of the next lecture to explain you these methods, which are very simple, and show you some examples, and then we're going to summarize afterward that. Okay, let's take a small break, eh? So what I wanted now is just to try to convince you about the simplicity of this boosting method here. And the one which we discussed before the break was first we looked at the regression case, and now we were looking at the classification case. And one way to find these parameters is to define an error. And then we want to find these parameters alpha m, which now define this function, which we want to boost and improve upon by from iteration. Then we just defined an error so that we maximize the inaccurate inaccurately classified cases. And you see that if you have a wrong classification, you get a positive argument to the exponential. So let's just rewrite this equation, and you will be surprised by the simplicity of the things we are doing here. I hope I can convince you about the simplicity. So if you now look at the equation which we had for the error, so this equation here, let's now just rewrite it in terms of a weight and the new function value. So I can rewrite this error as a sum over I, all the data points, which we are trying to classify correctly. So I can rewrite that one in terms of the old value. So I have a Cm minus 1 of x of I multiplied with E of minus, not gamma, but y of I. And this is now multiplied with a new parameter, alpha m. And then we have a function b of m of x of I. So this is just a rewrite of the function which we had before the break. And then I'm simply going to call the old value as a weight. So I'm just calling this as a weight of m. This is just a redefinition here. And then I can rewrite this error with an I equals 0 up to n minus 1. I have the weight here, which now carries information about the cases which are classified correctly and the misclassified ones. And then I have the new value, which goes like minus y, and then I have this alpha m, and then this function, the new function here of x of I. So we can split this one into correctly classified and wrongly classified. So we split into correctly classified and wrongly classified. So this W which we have is actually a weight which comes from the previous iteration, which means that this is just a constant. So this parameter which we see here, when we now have come to iteration m, this is just a constant, which carries with it information about correctly classified and misclassified. So we obviously, what we want, iteration by iteration, is to drive this weight to 0. But we are giving more emphasis in the training to the badly classified ones. So this is the basic philosophy here. And then if we do that, and we also recall that if we classify correctly, we have a minus 1. So if we classify correctly, this gives us 1. If we classify it wrongly, the argument and the minus sign gives us a plus. So what we end up with then is the following. So it's pretty easy to see that this would now give a sum where y of I is equal to this bm. So this is a prediction we are making, x of I. And we have a wi of m, the previous case, and e of minus alpha of m. So alpha of m is this parameter we want to define. And then I have plus, and then I have a sum over y of I misclassified, so b of m of x of I. And this contains the weight, wi of m, multiplied with e of plus alpha m. And it's typical when you start this iteration, because you would start with a value for the weights. And the typical way to start it is to put wi at 0, just equal to 1. So a typical starting value here is a w of I of 0, which is just equal to 1. So we give the same weight to everything. So what we're doing then is in the optimization, what we want now is simply to calculate d of epsilon error with respect to this alpha m, and we want to drive that to 0. That's the optimization which we are going to run. So you could say that our cost function now, if you now look back at what we have, this error defines our cost function. Okay? So you see now that you can actually play around with many, many different types of cost functions. So if we do that, if we just take the derivatives, it shouldn't come as a surprise that we get minus, and then we have a sum over y of I, the correctly classified ones, where this is equal to the value which this function gives us. And then I have my wi of m, and this is a e of minus alpha of m. And then I have plus the sum y of I, not equal to this bm of x of I. And then I have a wi of m multiplied with e of alpha m. And we want to drive this one to 0. And this is something which we now can set up. And remember now that this alpha m, this does not depend on the summation index I. So this parameter here, alpha m and alpha m here, they do not depend on these summations which when we loop over all the data. So these are just constants, right? So I can put them outside. So that means that what I get is obviously e to the minus alpha m. And then I have this sum over y equal to bm x of I. And then I have my weight wy of m. And this is equal to e of alpha m. And then I have the new sum here of y of I different from b of n, of wi of m. So these are just two different sums. And then the easiest way to find the alphas is to take the log of the functions on the both sides. If I take the log, then you will quickly find, when I just reorganize a little bit, you will find that this alpha of m is simply equal to 1/2 of the log. And then you have a sum over the correctly classified ones, y of I, equal to bm. And then I have a wi of m. And this is divided by y of I different from b of m. And then I have a wi of m. Now, what I could calculate now, I can actually calculate something which I define as the error rate, which is pretty common to set up. So we can define, so if you look at define error rate, and that gives us an epsilon m, which is defined in terms of the misclassified ones. So b of m of wi divided by m, and then it has a sum over all the correctly classified ones, y of I, or rather I. We start with all the values which we have. So I equals 0 up to n minus 1. And this is for all the data which I have. So this is the error rate, the number of misclassified divided by the total set of data which we have. And then I can rewrite this alpha m here as 1/2 of log of 1 minus epsilon m. It's not difficult to see that, divided by epsilon m. So that means that every iteration, we would then calculate this alpha of m. When we have alpha of m, we go back to the simple function b, which we have set up, and then we just keep iterating and calculate new alpha m's. And at the end, we would like this misclassified part to go to 0. And this is adaptive boosting, or ADA boosting, or just ADA boost, as it's called. So if we want to set up the algorithm in that case, And as I said, you can use different types of functions here. So the algorithm for ADA boost. So let's just set it down here. So the algo for ADA boost is actually pretty simple here. So we would have a data set, which we need to set up. Data set, and this is D. So we have our x0, y0, x1, y1, up to the final one, xn, yn minus 1. And then we initialize the weights. And they are normally initialized to 1. So we would have wi 0, and we put them to 1. We need to define the error function. And the error function is our cost function. So this is the cost function we want to optimize. And the simple function which I put up is one of the many choices. There are, if you look up the literature, you will find many, many other ways to actually to grow the importance of the errors. So the whole thing here is that you want to give emphasis to the errors, the misclassified ones. So in every iteration, you put more and more focus on those cases which are misclassified, which means at the end, you have very few cases which are misclassified. And hopefully you have 0 cases which are misclassified. So when you do that, you also need to define a weak learner. So this will be a function B. This is often taken as a decision tree. And a decision tree which is pretty shallow, which means that you have a function, a weak learner, which is easy to train, but which gives you a fit to the data which may be only slightly better than tossing a coin. And then you would start the iterations for I equal 1 up to the final one. Then you would optimize this error function, this epsilon of error, which in our case contains the weights. In our case, this is proportional to let's just leave it out here. We don't need to specify it. So this function here gives us then this parameter, alpha. So when we optimize it, we find alpha m. So we calculate alpha m then, which is given by this relative error. So this is given by a log. And then I have 1 minus epsilon m of epsilon m. Then I update. I found this value. Then I update. Actually here, we don't need, depending on the function we want to optimize, like in this specific case, which I showed you with the exponential, then there is no reason to calculate a gradient because we can just set in the expression for this alpha of m, depending on how many we classified correctly and how many we classified wrongly. So we would update this function c of m of x, which is now given by the previous value, m minus 1 of x, plus alpha of m, multiplied with the b of m of x. Then, when I have done that, I need to update the weights because I will use that in the next iteration. So the next step here, when we have updated the function c, is actually to update the weights. And in that case, I have a wi of m plus 1, which is simply wi of m multiplied e with e of minus 1 alpha m of bm of x. So now I have updated the weights. It's common to renormalize or normalize the weights. So we would typically also normalize the weights, so that they don't blow up in size. So we would then have a sum over I equals 0 to n minus 1 with a wi of n plus 1. So they would typically be summed up so that they're normalized to 1. And that is to hinder that the weights just grow up. Because if they become very large, this is a process which will have problems in converging. So it's just a way to renormalize it at every iteration. And then we have N4. And then we return the Cm of x. And then we have an optimal fit to the data. But it's actually, we had, I don't know if this sounds intimidating, but after I presented this in a lecture, I think it was last year, there was a participant in this course actually who programmed that one in just one of the lab sessions, because it's so easy to set up, as long as you have a decision tree algorithm. So that person just used a decision tree as a weak learner and just coded these expressions, and then had something which was comparable to what scikit-learn gives. So this piece of algorithm is extremely simple to implement. I hope I've been able to convince you about the basic philosophy. It's a simple method just to boost the quality of a function by iterating and optimizing in every iteration. In this specific case, you don't even need to calculate gradients because you have a simple analytical expressions for the new parameters. The only thing you need to do is actually to update the weights and the function values and just keep going, because you have an analytical expression for the derivative of the cost function, which in our case is just this error function, where you put emphasis on the misclassified cases. Okay, so I just wanted to show you some runs here, and then I'm going to briefly say something about the boosting methods. So let me just go back to the Jupyter notebook here. So I wanted to show you a simple application of ADA boost. And there is a function in, so this is basically what we've gone through now, and the basic algorithm where we ended. And there is an example here. So there's an ADA boost classifier. And you see now that the decision tree classifier is a pretty bad one. It's just a max depth equal 2. So this is barely beyond tossing a coin for a binary case. So we've been discussing the binary cases now. And we use that as a weak learner. And if we now just run it, you will typically see that this is actually pretty good. This simple method. So I get a 99% accuracy and 98% accuracy on something which is extremely simple to implement. Now, what I wanted to say something about, and I'm going to do this briefly, is about the gradient boosting. So you see the curves and everything. So gradient boosting, let me just give you the basic algorithm here. So if we take a steepest descent, which we discussed a little bit earlier, so if you think of the mean squared error, again, as a function, the recipe here now is actually to let this function here, f of n, be defined by an approximation which is given by a constant, this rho of m, a scalar, and the gradient, where the gradient now is calculated as a gradient of this function f at the previous value. And that means that, so it's essentially the same kind of boosting technique. You start with a simple evaluation, and then you keep improving upon the results. And then what you end up with then is a function now where you have the gradient here multiplied with a constant. And then you optimize this function here by finding the optimal value for this parameter gamma. And then you keep going and then simply have a new gamma, which is the minimization or the optimization of the function you have as a function of this specific function h of m, where you also start with a initial guess of this f, which now is going to be given by these gradients here. And if you use a steepest descent, this is one of the ways of doing it, but the steepest descent is not much used because it only optimizes f at a fixed set of points. So you do not learn a function that can generalize the results. However, you can modify this algorithm by fitting a weak learner to approximate the negative gradient. And what you can do then is, instead of using a steepest descent as I showed you, is that you would compute the gradient here of that function at the previous function value. But now you use the base learner to be the negative gradient. So that means that it's the gradient itself which is being trained. And then you would just keep iterating that. So instead of you having a specific function which you plug in, you're actually training the gradient of that specific function. And the idea then is that this will allow you to train a function in a more efficient way than we did earlier. And gradient boosting, if we now skip the regression case and look at the, so this is plain gradient boosting, it's not extreme gradient boosting, but the way you would train it is now to use gradient boosting here and classify it. So you also have a weak tree here, max depth equal 3. And if we run that, you will now see a result which is okay. So the test set accuracy with gradient boosting and scale data is 98% when you take the true positive and true negative, so which is also not so bad. But then there is another alternative, which is gradient boosting. So gradient boosting for extreme XG boost. XG boost is not a new method, it's gradient boosting, but it is actually an optimized gradient boosting library, which is designed to be highly efficient. It implements machine learnings under the gradient boosting framework, and it provides a parallel tree boosting that solves actually many science problems in a fast and accurate way. And so this is a library, and you would actually have to download this library to your laptops. So this doesn't follow scikit-learn. It's an independent library, but it meshes well with scikit-learn. So you can use all the functionality in scikit-learn. And then if we now, I'm going to skip the regression case because they don't do so well on regression cases. They do excellently on classification problems. That's my experience. So if you come across cases where these do well on regression cases, let me know. Those cases I've studied haven't been impressive. Actually, many of the deep learning methods we have encountered do a much better job. But in this case, you would simply now load it in as an XGB, and you would simply use the XGB classifier for classification problems. And I'm going to plot the same metrics. You remember last time we discussed, during the lab sessions, we discussed this scikit-plot library, which allows you to plot the confusion matrix based on your test data and your prediction on the test. It allows you to plot the ROC curve or the cumulative gain and many of these other ways of displaying the quality of your model. So if we run that one, you will now see something which looks like this. And this is on the Wisconsin data set. So you have a perfect classification. So it's actually pretty impressive. And the methods are extremely simple. So if you got the philosophy of add a boost, instead of having a function you predefine and you train again and again and boost, you would actually use the gradients. And that's the gradient boosting. And the philosophy is extremely simple, and it's easy to implement it yourself. And you saw these steps with the ADA boosting, and the same steps with gradient boostings are very easy to set up. If you have the framework for ADA boost, then to replace the function you boost with a gradient is actually very straightforward to do. So if you're tempted to do something like this for the final project, feel free to do so. Or we've had people who studied the bias variance trade-off using the different random forest methods or bagging methods or different ensemble methods, and then just looked at how the let's say the mean squared error or the classification error behaves as a function of different decision trees methods, ensemble methods like random forest, bagging, or boosting methods. So this is also an alternative for project number 3, if you're interested. As I said in the beginning, I mean, depending on what you want to do, just please send us an email in case you are a little bit in doubt whether this case is something which we think is enough for project 3 or not. Okay, any questions so far? So this part is going to end the, how to say, the course here. And I just want to give you a quick summary. We're going to not use much time. I always like this one. And you've probably seen, some of you have probably seen this figure. This is the way I felt exams were when I was a student. And in Trondheim, what happened there is that every spring, when all my friends, which I played soccer with and were not students, were having a good time, the weather was nice. You were sitting indoor and just struggling with different exams. And then when you were done with exams, the weather turned crappy. It even snowed in the beginning of June, right? I said, no. May was a beautiful month, but then we were just indoor. And I often felt like this, 1 week before the exam, and then 2 days before the exam, and then after the exam, it was like this. So hopefully, in this course here, you don't experience that. So having a project-based work is actually much more fun, actually. What I want to do now is to change a little bit to the, just let me change to the, I don't want to use the Jupyter notebook here, but I want to, let me just see, where did I put that one? Not here. Let me just bring this up with the right one, because I wanted to use the, let me just bring it out. So let me see if I can share it properly with those of you online. So share screen. Sometimes my browsers disappear here. Oh, there we are. Okay. So I just wanted to use these slides instead of the Jupyter notebook because sometimes it's easier to read these. And if we now look at what we've done, there are some links here for more inspirations and further studies. But what we have focused on is actually a lot of optimization and statistical learning. And there is the artificial intelligence, when we think of that, is a collection of the way we've looked at it here. If you think in terms of artificial intelligence, it can be defined in 2 different ways. One, as a collection of machine learning algorithms. So if you have self-driving cars, there are actually several machine learning algorithms operating. Or you can actually have artificial intelligence without machine learning. So our emphasis has been on machine learning. And that means that we've tried to make fit the functions or make predictions and then find correlations in the data sets. So I wanted here just to point to some further things. So one of the topics which is very, very hot nowadays is Bayesian statistics and Bayesian machine learning, where you try to get the best from both worlds, which means that you would like to have a probability distribution which describes your data. When you have a probability distribution which you have trained, you can also predict the errors. on both the parameters and the variables which you want to predict. So that means that you will train a model and you can also come with an estimation of the errors, which is normally not the case in what we have done. So we focus more on actually reproducing some data which has been labeled. And this has been the kind of traditional path in machine learning. So when I'm saying these things, it's mainly because I wanted to point to other courses, but also to actual research. And if you think of generative models, and I guess nobody has not heard about ChatGPT. So generative models are actually based on this philosophy where you train a probability distribution. And I just wanted to point to you to courses which actually deal with that after you've gone through the basics now. So if we look at, I'm going to skip some of this. So the topics which we have focused on in this semester has been mainly statistical analysis of data, optimization, and then clearly machine learning has been central. And there are things which we haven't discussed much, and other things which we have discussed, and you can see a list of the topics here, like the principal component analysis is something which we haven't discussed as a way to reduce the dimensionality. But we've looked at cross-validation, bootstrapping, we've looked at gradient methods, central elements from linear algebra, and many, many other things. And then the methods we've looked at are those which you see here. We've done linear methods for regression and classification. We've looked at neural networks. We've looked at decision trees, but we have not looked at support vector machines, but you can find them in the lecture notes if you wish to look at them. So you could say now that the first one belongs to the pre-deep learning methods, the deep learning revolution methods, and the same applies to number 3 and 4. So support vector machines were actually developed in the 90s, in the previous century. And if we look at the kind of learning outcomes, we obviously want you to understand the basics of linear methods for regression and classification, neural networks. As I said, support vector machines have not been covered. Be capable of extending the acquired knowledge to other systems and cases. And we want you to have an understanding of central algorithms which are used in machine learning. And if you now look at deep learning, we actually put a lot of emphasis on you writing your own neural network code. And the reason for that is that the backpropagation algorithm is at the heart of basically all deep learning methods. So if you're using autoencoders, you will have two neural networks actually competing with each other in a way. Same with the GANs and so on. And at the heart of these networks, like a recurrent neural network as well, there is a backpropagation, whether you do backpropagation in time or just plain backpropagation. So that basic philosophy is something you will see being used again and again in all the deep learning methods. So clearly also calculating derivatives, even if that doesn't sound too exciting, with tools like automatic differentiation, is something which you will encounter again and again and again. So we put a lot of emphasis on that, and also put some emphasis on other central algorithms like logistic regression, and also some of these decision trees and ensemble methods, which you will encounter in many, many applications. And so it's actually a field where it's very, very difficult to actually follow what's going on, because there are tons of scientific articles popping up every day. And you have companies like Google with DeepMind, which has an annual budget, wage budget of billions of dollars, $1.2 billion in 2021. So sometimes you feel that it's very hard to compete with many of these big groups, but many of these big groups spend a lot of resources on training their models. In that sense, at the university level, we can actually perhaps think more about how to make better algorithms, because the training is often the very expensive part. And I guess you felt that when you did project number 2, that the training part actually took a lot of time. And Google's DeepMind, for instance, just to mention one of the companies, has tons of software engineers which fine-tune the models and train the models. And that's where a lot of the money goes into in the training part with access to high performance computing facilities, which can train these models. So just to give you an example, there's a city in Oregon, which was very happy to get Google's high performance computing facility there. But that facility took 80% of the electricity of the town. So they didn't have electricity for their citizens. That's just an example on how intensive many of the training of the models actually can be. So you should think of, I think the fun, to me, the fun part is actually the one where you develop algorithms and test the mathematics, study the mathematics and so on. But clearly without being able to train it and obtain an optimal reproduction of the data, you may feel that it's less worth it. But this is a balance we have to strike between how much time we want to spend on training and how much time we want to spend on development. And I think there is place for a lot of space for everything here. There are many places you can follow new preprints, and one of the standard one is this preprint server Arxiv. If you follow there, you will see that there are tons of articles every day. This is just a list. You can look up these lists. And I'm going to skip some of these because we've been discussing this again and again. But I wanted to mention some of the courses which we have. And there are several courses if you're interested. So we have one which is called Advanced Machine Learning and Data Analysis, which actually focuses on deep learning methods. And it has a part which deals with a further study of convolutional and recurrent neural networks and autoencoders. And then it has emphasis on generative models. So generative models are models where you actually train a probability distribution. And these are often unsupervised algorithms. This is something which we haven't touched much upon in the semester here. But the training a probability distribution is essentially the basic philosophy behind ChatGPT. But in this course, there is more emphasis on application to natural science problems by obvious reasons. And we have a basic course which essentially focuses on linear regression and logistic regression. But we have one course which is called IN, where did I have it? No, I had changed. This is a new code actually. So the, I thought I had changed that one. So we have this course which you see here, you can click on all of them. This has actually changed name now, and it's called Deep Learning for Image Analysis. And this runs in the spring semester. And you can see that as a follow-up of this course. And many of you may actually go in directions where you want to classify and recognize images. And this is a course which actually focuses on that. As you can see, it's a deep learning for image analysis. So the focus there is very much on things like convolutional neural networks, autoencoders, recurrent neural networks as well, and many of the techniques which we have discussed. So the course actually assumes that you have a knowledge similar to what we have here, because they typically spend just one day or one double lecture on linear regression, and then another one on neural networks, and then they jump immediately into convolutional neural networks and discussions in depth of these methods for image analysis. So this runs in the spring. So having this course actually fits very well for that course. So if you're interested in that topic with image analysis, I would normally say that that's a pretty good choice actually. And there are many people who actually follow that course. We also have, as I said, this course is more tailored to, say, the solution of problems in the physical sciences, often with a big emphasis on solution of differential equations, with physics-informed machine learning, for instance, which is a very hot topic, and also on how to develop generative models for studies of physics problems or problems in the physical sciences, which means geoscience, chemistry, physics. And some of these methods can also be used on, or actually many of them are used in, let's say, computational neuroscience, which is a pretty hot research topic. So these are all possibilities for further studies. This is actually a course which I think this runs in the fall. And this is also a very popular course, which many people have taken, as this one, but this is parallel to this one, so you would probably recognize many things there. If you're interested in more statistics, we have one on computational statistics. Unfortunately, the other one on Bayesian statistics runs in the fall semester, unfortunately. But that's also, if you're interested in Bayesian statistics and numerical methods, this is also a very interesting course. So this is just some few suggestions on topics which could be follow-up topics if you're interested in machine learning. So what's the future like? Now, when I gave this seminar last year, ChatGPT was just in the shaping. And there's been a revolution after that. So I wanted to keep that one just to tell you how things looked like last year before ChatGPT. And you would see now typically that recurrent neural network, convolutional neural networks have made a huge hit in the market, have been extremely popular. These so-called autoencoders, which is often also used for image or sequence generations, machine translation, text summarization, image captioning, and much, much more. I think using ChatGPT, for instance, the generative models in your research, and also when you're following courses, is a fantastic tool. I hope some of you have been able to use them in writing the reports. It's often a very useful tool where you can ask questions, and many times you're back home and you don't have the possibility to be at the university and ask people, and then you can actually use that one as a partner to ask questions. And sometimes the answers may not be very good, and then it's you with your knowledge who has to assess whether this is a good answer or not. So it means that it requires that we have a better understanding of many of the algorithms. And this has been a little bit of the philosophy here, that we try more to focus on the basic algorithms and the mathematics behind many of these methods. I know that many people feel a little bit disappointed because at the end we tune many parameters. But on the other hand, there is actually, when it comes to deep learning, the field was actually almost dying before the universal approximation theorem was developed. And then with that one, that gave a lot of, how to say, legitimacy to the neural networks and deep learning methods. And then in 2010, roughly, when Ben Zhou et al. Came up with a deeper understanding for why neural networks didn't train well due to vanishing gradients or exploding gradients. And then they found a cure to that and a better understanding. Then the field has simply exploded in the last 10 years. And it's no wonder that machine learning is actually used in many, many different disciplines. It's actually used everywhere now. And institutions which have been leading are institutions like CERN in Geneva, which is actually particle physics, but they have a huge computer science division. And many of the algorithms for analyzing tons of data have been developed by computer scientists, physicists, mathematicians, et cetera, in environments like CERN. And if you are analyzing data from many, many experiments nowadays, you can often have terabytes or petabytes of data. And there is no way you can actually run through all these images yourself. So if you have 1 gigabyte of information and you want to run through that, and it takes you, let's say, a minute for every image, and you have a gigabyte of images, then you can do the counting and find out how much time you will need to analyze 1 gigabyte of images. And these are things which you can automatize. And I think this is very important to keep in mind. So when we do science, this is an extremely useful tool in the data analysis. And when you look through the slides here, I'm not going to keep you more here. There are tons of things you can take a look at if you want to. I have discussions of Boltzmann machines, which is actually a very simple way of setting up generative models. So a Boltzmann machine The reason for why it's called a Boltzmann machine is that we are training a probability distribution which looks like this. And where the parameters are given by the weights and the inputs. And you're trying to train a probability which has a normalization constant, which is called the partition function. And this is based on a physics-like problem. But this is one way to train a probability. So you would train a probability to reproduce specific problems. And then you can use this probability to generate new instances. And this is the basic philosophy of algorithms like ChatGPT or other algorithms which are generative ones. You could train it on images of cats, and then it can make a new image of cats which were not in the training set. And a Boltzmann machine is actually one of the simplest possible ways where you can set up a network where you have some hidden parameters. And the way you do this is to define a function here, which is then inspired by physics in a sense. So you will have some weights here, which connect the hidden layer with the input layer. So there's normally just one layer because it can be difficult to train. And then you would change the output continuously, or you can have a fixed output and you want to optimize a specific function. So at the end, and I've been using this in quantum mechanical problems, and then I would say that the wave function squared, which is the probability in quantum mechanics, is given by this Boltzmann distribution. And I train it so that I can optimize the energy of the system. That would be my cost function in that case. So Boltzmann machines are some of the basic machines which are used in this kind of field. And if you go through here, you have there's a link to autoencoders, and if you want to read more, I just leave that as a kind of how to say addition. If you want to look at these videos, these are covered by many of these more advanced courses. We have video on Bayesian machine learning, and for every one of these reinforcement learning, I'll put some lectures and videos, and you can take a look at these things. So I'm not going to bother you with more things like transfer learning, adversarial learning, etc. And I think I also had a link. There's actually I can say, if you're interested in generative models or generative deep learning, just let me know. And feel free to take a look at this. In science, there's something which is actually a very interesting thing, and it's called scientific machine learning. And this is close to what we call digital twins, where you actually have an implementation, a real implementation. If you think of a windmill park, you can have the actual windmills, and then you have a software which governs the windmills. But then the windmills have sensors, and these sensors can feed back to the software. So you can update the software depending on the kind of inputs you get from the sensors. So this could be you adjusting the windmill according to wind directions, etc., etc. And scientific machine learning deals often with both developing fast applications and also that means software and also computing architectures. This is a pretty hot field actually. And this is something which is used in tons of different disciplines, from medicine to particle physics or detective development and so on. So feel free to take a look at some of these references, and I'm not going to pester you with too much here. I just wanted to end with some statements here, which I put up in the beginning of the semester, and feel free to take a look at them. Some of them are pretty, how to say, bold, like the third one, which says that in the long run, AI is the only science. There is a good textbook on artificial intelligence by Russell and Norvig, where they say that's relevant to any intellectual task. So I leave this up to you to judge these statements and have your opinion about them. And if you wish to read something when we get close to the winter break, and you want to have a critical eye on machine learning methods and machine learning and AI, there is actually a very good textbook by Kate Crawford, which takes a critical look on many applications of machine learning. So we haven't discussed the ethics of machine learning in this course, and we focus more on the mathematics and developing codes and understanding what goes on. So The ethics of machine learning and AI is something which is a very, very important issue. So feel free to discuss these things. And if you wish to get a start, Kate Crawford's book is actually pretty good. And then, as I said, it's always sad when the semester is over, but it's been a true pleasure to get to know you all. Thanks for coming. And thanks.